Right. Let's start with factors. So with this factors, our notation is going to be okay. Oh, this one. Use this. Factors. Say this is the point A, and B, so point A and B. This is point. And this factors is denoted as A. See? See, if I write this down using just a parentheses, regular parentheses, then this is a coordinate. This is a factor. This is factor. Okay. And equally, it is written as A times factor I and B factor J. Yeah, like in physics. A and B is, I and J is this. This is I, factor J. Okay, while I here is this vector. And J is this vector, 0, 1. Okay. And let's see. In 3D, oh, sorry, it's quite similar. Okay. So you have this vector. Okay. So in terms of this, the endpoint is, say the endpoint is this coordinate. Then as a factor, the factor is written as A, B, C. And this is same as A times factor I, B times factor J, and then C times factor K. So I here is the factor 1, 0, 0. So 3 components now. J is 0, 1, 0. And K is 0, 0, 1. Okay. X, Y, Z. Okay. So that's, we can do operations, operation on factors. Okay. For example, you can do arithmetic operations. You can add and subtract factors. So say A1, B1, C1. And you have two factors, A2, B2, C2. Okay. And you can subtract. Well, that means you just add or subtract 1, B1, and C1 abstract C2. Okay. Or you can multiple A. Oh, that's yes. It's like a factoring out the each component of the factor. Okay. So same thing with with two components or three components. This operation is the same, exactly the same. And geometrically, this means we have this vector. Uh, um, take vector. Okay, so this is AB. Well, I'll go back and forth between a plane or space, doesn't matter. Okay, and we have this ladder. Say this is uh, say this is vector ABC. One. This is vector A2, B2, C2. So addition vector is like the oh, sorry. A1, B1, C1. Let's copying this one here. So you get this is the same as this one. Then the sum is this one here. This is the sum. Okay. So suppose this is okay. V1. This is vector V2. Then the green one is V1 plus V2. Okay, so that's the meaning of the. What about subtraction? Well, subtraction is uh, 2 feet 2, for example, here. Then this is equal to V1. Okay, so just extend extend a factor. This is negative. This is negative. This is negative. Negative V1. Okay, so other opposite direction is V1. So V1 minus V2, for example, it's the same as V1 plus negative of V2, opposite of V2. Okay, so in that case, it would be, they say this is opposite of V2. This is opposite of negative, opposite of V2. Then this one's going to be this way. Okay, so the negative is just here. B1 minus B, because this is minus B. Okay. So that's a geometrical uh, intuition of a graph. Sorry, factors, addition, subtractions. All right. Same thing with the factors in space. Just make comments here. Oh, this is wrong notations. I should say this is factors of two components only. So there's no C in this case, in this picture. But even with C, the rules is similar. Factors in space. Okay. Questions? Okay. And we can find length of vectors. B, say this is A, B. The length of vectors is just the norm of the vectors. It's defined as the A square, B square plus C square, square root. Okay, so that's the length of vectors. Okay. The unit vectors mean length 1. Okay. And the vectors can be normalized in terms of can be, what does mean normalized? Normalized means that uh, the length can be made 1. The normalized is this one. Given B is this vector ABC. So normalize. Okay. But to normalize is that's easy. The normalize is the unit vector is say with tilde is just the original V divides by its north, by its length. Well, we see that compute the length of V. Well, the length of V is the length of over, well, the length of length is just length. Length of V is just the length of V. So it's just 1. Okay, so this is a normalized version of V by dividing by the length. Okay. Okay, another operation is what we call a dot product, or a what we call a scalar product. Now the tricky part is that this is one. When I mentioned operational factors, this is just addition, subtractions, multiply by a scalar, but no multiplications. There's no multiplication of factors. Well, dot product is multiplication, but it's not multiplications in the sense of numbers. Let's see. If you multiply a factor by a factor, you expect something, the product is a factor. Okay? But dot product doesn't give you factors. For example, here, uh, let's see, uh, uh, B1 is A1, B1, C1, B2 is A2. So what we call the dot product is here, dot product. So this is defined as the sum here, A1, A2 plus B1 times B2 plus C1, C2. Okay, so in summation form, this is K1, 2, 3. So because three components, uh, say, I should say, oh, later I'll use this one. If it's just a in the plane, then just dismiss the C component, the third components. Okay. So what does it mean? And I want to show you that this is actually the formula that uh, you have from high school. What's that? Length of B1 times length of B2 cosine alpha. So alpha is the smallest angle between factor V1 and V2. Okay, so that's the same. So the thing here is that V1 times V2 is a number, not a factor. Okay, so in that sense, that product doesn't give you a factor as like if you multiply a number by a number, then you get another number. Okay, so it turns to be another species, not a factor anymore. Okay, so this is not a real product. Okay, so what does it mean here? Um, okay, so let's see. Geometrically. Geometrically, in plane. Yeah. So let's make this easy. Uh, all right. Both we have. So let V2 is just a unit vector. We have this V2. This is V1. Uh, all right. So you see this length of V1. Let's see, this is assumed V1. V1 cosine alpha. Alpha is this angle here. So the cosine part is the, say, the horizontal part of this angle alpha. That means you're going this way. Okay, so alpha here. So you have this length. Uh, so this is projection. Oh, projection of V1 onto V2. The length of projections is actually V1 cosine alpha. What is this? Well, this is nothing but so dot product you can think as projection of V1 onto V2 or the other way around. V2 onto V1 is or V2 onto V1, the other way around. So that means the what mean by the dot product. And the nice thing about dot product is that because V1 dot V2 is cosine, right? Now, if the cosine is 0, okay, so that meaning that alpha equals pi over 2, 3 pi over 2. Okay, so that means V1 is perpendicular to V2. Okay, so we have a criteria for perpendicular. Two factors are perpendicular if the dot product is 0. And so that's the easy one. So example, given V1 is A1, V1 is just a number. 2 minus 5, 3. And V2 is 3, 9 alpha. Okay, so the question is, we need to find alpha so that V1 perpendicular to V2. Okay, so that means what is This means v1 dot v2 should be 0. Okay, so in this case, we just compute this v1, v2. This is 6. Here minus 45 plus 3 alpha equals 0. And then you can solve for alpha. Okay, so alpha is, let's see, this 45 minus 6, 39. 13. Okay, so let's give you uh, a criteria for perpendicular. Okay, questions? Let's go to the uh, coordinate system. Right. Let's go to other operations. All right. So perpendicularity is also correct for vectors in the plane. So it equals 0. That product equals 0. That's perpendicular. Okay, so that's the same thing. Now we have another operations, what we call a uh, cross product. Now for cross product, uh, must be in space. So cross product always involving factors um, in space. So 3 components. Two is A, 2, B, 2, B. Okay. All right, so cross product is this one. Okay, so this determinant of this matrix. So you make this matrix. So this is factor I, K, K. So yes, this is A1. Sorry, B1, C1, C2, determinant. All right, so we haven't got to this point yet. So determinant of a matrix. Okay. So how we compute this one? All right, so there is a rule here. For 3 by 3, you can proceed this way. There. But then you have to, do you remember this method? Computing determinant of a matrix 3 by 3. Let's do this one. Uh, 3 by 3. Okay. If 3 by 3, then you have A1. 1A1 2, A1 3, 2 1, A2 2, A2 3, 3 1, 3 2, 3 3. Determinant is, well, pretend you copy the first 2 rows, sorry, 2 columns. A1, A3, 3, 2. Just pretend this one you have. Okay. And you kind of multiply by this. This gives you plus, plus, plus. You add. And then you have this with minus. Okay. But this is only for 3 by 3 now. Okay. So you get A1, A1, sorry. This first part, A11, A2, A13. Okay. Let's see. Plus A12, A23, A31. See? And plus A13, A21, A32. Okay. And the minus is here. A13, A22, A31 minus ladder A32 and minus 2 A, what is that? 2, 1 and A3, 3. Okay, just remember this one. Yeah, ask questions.
Yeah, I have a question. Is that the entire cross product, or is it? Is it with both the plus and minus for both the cross product?
Yes,
Is it like one equation?
all of this. And if you're going this way here, follow this for plus sign. So you add and follow the other diagonal for the minus sign.
So the cross product is the sum of all of this.
Yes, sum
Okay.
of all of this. Okay, it's kind of complicated, but you can. Okay, so this going this way. All right. So the I, we call this I. So here is B1, C2 going this way, but you subtract because this is I here. So subtract this one. Subtract B2, C1. There we go. Okay. And J is C1. Here you have A2, C1, A2, minus going this way, A1, C2. And the K is, let's see, pretend you have A1 and B2 minus B2, A2. Okay. One, right. This is one. This is one. Okay. Okay, so let's do the some example. So this is I, J, K. So it's 2, 3, -1, 1, 4, 1. Okay. So the I is uh, 3 times, this is 3, minus minus 4. So plus K. K here is -1, so just 1, minus 2, 1. K. K here is, let's see, 2 and 4, 8 minus 3. So plus, there you go. Okay, so okay with this one. There is another way to find the determinant. Actually, that is the general rule to find the determinant using cofactor. But I'll tell you the next time with this. Okay. And if you uh, for factors in a plane, assume the third component 0. Okay. So for example, if V1 is say 2, 3, and V2 is -1, 5, for example, uh, V1 cross V2 is this one, 2, 3, 0 here. You assume uh, the third component is 0 because that's on the plane. So the Z component is 0. Okay. So then what you get is that, see what you get, I, J, K, 2, 3, 0, 1, 5, 0. What you get is I, let's see, 3, 0, minus 0, 5. Okay. And K part is 0 times 3, that's 0. And 2 times 0 is 0. K part is times 5, that's 10. Minus 3 times minus -3 plus 3, 13K. Meaning what you get here now is uh, a factors in space. So going outside you work with the, say, this is a plane. This is an XY plane. You have this B1, B2, but the cross product here is there, going there. Okay. So Let's see. Before we stop, let me just mention two properties. Uh, the peculiar thing about the cross product here is that V1 cross V2 is not the same as V2 cross V1. In fact, if we use examples later, that this is negative of. So this is odd because you don't have commutative. You multiply numbers and you can switch the order. Okay, 5 times 4, that's the same as 4 times 5. But this one, if you switch the order, you get negative signs, so the opposite directions. Okay, and let's see what else. What I'm saying is that V1 plus V2 always perpendicular to V1 and also perpendicular V2. Right, so that's why when you have a two factors on the plane, xy plane, right? So the product V1 cross V2 is factors only have k. This is what we have here. In fact, you can do this in general. You have two components, AB, A1, B1, A2, B2. Then you have the product is just factor in k components. Right? So going outside the plane. All right, questions? Okay, if not, then let's stop here. And I'll share the note as well as the record. Okay, stop.